Hi, my name is Campbell Lachlan, I'm from Australia, and I'm going to explain what an electron is, because no one has done that correctly up till now. Now this is quite different to what you've read, so listen carefully and think about it for a while before you make any judgment. Science says that an electron is a fundamental particle, but this is not so. Science also says the electron has no structure, and science is plain wrong, and I'll tell you why. Electric charges are the fundamental entities of the universe. We can't really call them particles because they're not lumps of stuff, and I'll explain what they are later. A charge is a point of no size, always with an electrostatic field, and if we could shrink ourselves as small as 10 to the minus 50 of a metre, it'd still be a point of no size and appear just the same as you see there. Charges are always moving. It's been well proven that a charge in motion will generate a magnetic field, and that a moving magnetic field will generate an electric field, which will generate a magnetic field, which will generate electric, and so it goes on to some asymptotic limit. And because of this, every charge is at all times surrounded by a complex electromagnetic field, and we can call this its L field, or just L for simplicity. Because of the well-proven facts I've told you, it is clear that an electron is correctly a negative charge combined with its accompanying L. And notice that it is not and can never be a lump of stuff. The proton is similarly a positive charge and its accompanying L, but this L, the proton's L, is actually 1836 times the magnitude of the electron's L. And why? That's to provide a practical working balance in the universe, and if you want proof of that, just look around everywhere. It works well, doesn't it? The actual sizes of the different L's seem to be much the same, but the strength of the proton's L is greater. Now if we accelerate a charge fast, for instance an electron in an accelerator or a cyclotron, will cause an imbalance between the charge and its L. You can see I've drawn it there a bit eccentric, which results in a small force trying to restore the charge and its L to equilibrium, and we call this force inertia. Notice, no lumps of mass, stuff or anything else. Now for a bit of school. If we apply a force F to a charge over a time interval t and measure the velocity v, before and after the time interval we can measure its acceleration a like this. v2 minus v1 over t equals a, the acceleration. And then, because we know the force F, we can calculate a derived quantity m like this. M equals F on A equals a figure, and we call that the rest mass of the electrons. Note, still no lumps of stuff. Now, mass is a derived measure only, and it's not a reality. You've got to remember that. It's hugely convenient for maths, but that's all. And because all electrons are exactly alike, their L's and derived masses are called universal constants. Now if we accelerate an electron very, very quickly, some bits of the L will release off the tail end of the L in the form of photons, and it is a well-proven fact that accelerating charges emit photons, but the precise mechanism has not been known until now. These photons are closed-loop bundles of electromagnetic energy and will travel indefinitely until they interact with something. When they interact, if conditions match up, the closed loop will open and confer its energy and momentum to the recipient, which increases the recipient's activity, which we measure as heat or kinetic energy. Notice, still no lumps of stuff. At the instant the acceleration stops, the lost L is replenished from the source behind the charge. This source is what powers the entire universe, and charges are simply portals to that source. Hence their permanence and why they have no size or structure. We see examples of what I've described in events like explosions, where tightly packed charge L combinations, when forced by some input like a spark or detonation, stage a chain reaction until the internal acceleration is reduced sufficiently. Now you're getting a simplified version here, leaving an uncontrolled mess of heat, noise, light and damage in its wake. And the question is, what can we do with this knowledge? Is it of any use to us? And the answer is yes, it is. If we can control the chain reaction, we can generate clean, cheap, limitless energy safely. And we can do this. How? by oscillating electrons extremely fast in a control space, which means at an extremely high frequency. And this symbolic sketch shows what happens. Got an electron moving in that direction, it's decelerating towards the pole, the charged plate, shedding photons, and accelerates away, shedding photons. In the middle here, it's at maximum velocity, and then decelerates again that way and accelerates again, shedding photons, because it works both ways. By this way means we're in a sense harvesting energy from controlled explosions. We're taking energy almost, but not quite directly from the source, instead of the laborious multi-stage processes that we use now. For instance, proteins, and CO2, and sunlight, trees, rain, rotting trees turn into coal or oil, whatever, and then we burn the stuff. And all of that takes millions of years. By the process I'm talking about, we do it almost instantly. And most importantly, because we involve no neutrons or transmutations of elements, this is a clean, non-nuclear process which produces no dirty residue, as does fission and fusion. It's as simple as that. Let's do it. The main problem is that current technology limits us to an oscillating frequency of about 1 gigahertz, and we may need higher than that, 10 to 1,000. So there's some work to be done. Let's do it. So you know what it's all about. I'll follow the series as you see there, and if you're interested, send us a note. Bye.